The release of toxic constituents from improperly disposed hazardous wastes has threatened human health and the environment by contaminating our nation's groundwater and surface water resources. To prevent this from occurring in the future, EPA's Office of Solid Waste developed the toxicity characteristic to characterize wastes as hazardous from the standpoint of their potential to release toxic constituents to the environment when improperly disposed. In developing this characteristic, EPA used, as a reasonable worst-case scenario for these wastes, co-disposal with municipal solid waste in an unlined sanitary landfill. EPA developed a procedure, Method 1311, known as the Toxicity Characteristic Leaching Procedure, to estimate waste constituent release under this mismanagement scenario. This video documents further development of that procedure to better estimate release for difficult-to-filter wastes. Method 1311 is a batch extraction procedure that was developed to estimate the potential for wastes to release toxic constituents if disposed in a sanitary landfill. In this context, release is defined as the passage of waste constituents through the layer of soil immediately underlying the landfill. Method 1311 models two release mechanisms that can occur when industrial wastes are co-disposed with municipal waste. Release in primary leachate occurs when the mobile liquid portion of a waste moves away from the waste and into the underlying soil. This primary leachate can consist of aqueous and non-aqueous phases depending on waste composition. Release in secondary leachate results when municipal waste leachate, formed as water infiltrates the landfill and percolates through the sanitary refuse, contacts a waste and dissolves toxic constituents. This aqueous secondary leachate then moves away from the waste and into the underlying soil. The potential for a waste to release toxic constituents in the combined primary and secondary waste leachates is defined as a waste's release potential. Method 1311 models these two release mechanisms to estimate a waste's release potential. To demonstrate, Method 1311 is applied to a synthetic waste consisting of a solid phase and a liquid composed of both aqueous and non-aqueous phases. The initial filtration step of the Method 1311 separates the solid and liquid portions of the waste. Here, the filter models the layer of soil immediately underlying the landfill. The initial filtrate may contain one or more liquid phases. In this example, the initial filtrate contains a yellow oil phase and a red water phase. Both liquid phases are retained for analysis as an analog of the primary waste leachate. The solids from the initial filtration step are placed in an extraction vessel and extracted with simulated municipal waste leachate to model the leaching process in a sanitary landfill. After an 18-hour extraction, the material is filtered. The filtered extract, in this case containing leachable red, water-soluble constituents, is retained for analysis. The filtered solids, here colored green, are discarded as they represent the portion of the waste that would be immobile in a landfill environment. To recap, the Method 1311 initial filtrate is intended as the laboratory equivalent of the primary leachate, while the filtered extract models the secondary leachate in the real world. Together, the initial filtrate and the filtered extract form the Method 1311 final extract, which estimates the total release potential of a waste. Although EPA has demonstrated that Method 1311 is adequate for a variety of wastes, some wastes, including many oily ones, have been reported to clog the glass fiber filter. This results in incomplete expression of waste liquids during initial filtration. In addition, filtration results from different laboratories were at times inconsistent for the same waste. The objective of this project is to evaluate changes to Method 1311 which would overcome its limitations when it is applied to hard-to-filter wastes. Robert Truesdale, a hydrogeologist at the Research Triangle Institute and the principal member of the research team, describes the approach taken to measure the movement of waste into soil.
The objective of this research is to develop a method that can predict the leachability of oily wastes when they are improperly disposed. Our first step in conducting this research was to determine how oily wastes actually move in the real world when they're improperly disposed. We felt it was not practical to conduct in-ground full-scale experiments because of cost and time that's associated with such work. We went to the next best thing, which is soil column experiments, to simulate the release of constituents from a waste into a soil. These experiments were designed to provide data on how waste constituents are released from a landfill in the primary and secondary waste leachates.
These data may then be used to evaluate the accuracy of Method 1311 in predicting the potential release of difficult-to-filter wastes from a sanitary landfill.
One of our first tasks was to select and procure waste for testing. We wanted to select a group of wastes that represented as broad a range of waste properties as possible. Creosote sludge was selected and procured from a wood treatment plant. This waste has a heavy, very viscous oil-water solid emulsion that has a consistency very similar to mayonnaise. Two commonly generated refinery waste, API separator sludge, and slop oil emulsion also were obtained. These wastes, although they are oil-water solid emulsions, have a much less viscous, more watery consistency than creosote. The final oily waste selected and procured was waste motor oil. As anybody who has ever changed the oil in their car knows, this is a very liquid, easily pourable oil that has a single phase. It's also perhaps the most ubiquitous and widely generated waste of those that we tested in this project. In addition to the oily waste, we selected latex paint sludge, which is a polymeric waste that has been shown to cause problems in other extraction methods that were designed to test a waste leachability.
Civil engineer Dr. Jeffrey Pierce of Duke University oversaw the design, construction, testing, and operation of the columns.
We very quickly went to the use of three materials, either Teflon, pure Teflon, or glass material, or stainless steel. So we have a system that's in use that combines a glass cylinder with a Teflon top plate and bottom plate with a series of stainless steel valves fitted with Teflon Viton O-rings connected with Teflon tubing. So we're chemically inert as we can possibly be.
We selected 4 soils for our experiments. These soils bracketed a range of permeabilities from 10 to the minus second centimeters per second to 10 to the minus 6 centimeters per second. They're representative of anything from a coarse, freely draining permeable soil to a more clay, less permeable soil. The materials we selected for these soils included coarse, very clean quartz sand for the higher permeability soils and fine ground quartz for the low permeability soils. Although soils often contain constituents such as clays and organic material which can sorb contaminants as they pass through the soils, these sorption processes largely affect just the movement of the constituents through the soils rather than the release or the passage of the constituents into the soils. Because we were modeling release with these column experiments, we decided that the cleaner sands and ground quartz would be better to minimize absorption. This had the added advantage of making it easier to extract oily waste constituents from the soils prior to analysis of the samples.
We went through literally months of preparation and pre-testing to determine how we could guarantee 2 things. We wanted to make sure that the soil column was reproducible. One column reproduced the second, reproduced the third, and so on, because we ended up making hundreds of these things probably over the last 18 months. And the second thing we wanted to make sure is that there was a reasonable uniform flow through the column. We didn't want to have one column with short circuits down the sides and another column with short circuits through the middle. So we prepared the columns and ran chloride tracer analysis on the columns to see if there was a nice uniform throw, and we were able to hit the bullseye pretty closely with our procedure that we defined. So we follow that procedure now in preparing the columns very closely, very tightly.
Dr. Pierce and his assistant, Jess Everett, will now demonstrate the column packing procedure. Using a long neck glass funnel, a measured amount of soil is added to the columns in 4 1-inch layers. Following the addition of each layer of soil, the column is tapped by hand while it is rotated. The tapping is carefully timed to ensure that each soil layer in every column is packed uniformly. As the sand is added to each layer, the funnel is rotated within the glass cylinder to ensure an even distribution across the surface of the column. Once the soil is completely packed into the column, a measured amount of distilled water is added to completely saturate the column. A measured amount of waste is then added to the saturated column through a funnel inserted through the column top plate. Once the waste is added and smoothed to an even surface, the columns are wrapped in a plastic shield to minimize the degradation of organic compounds by ultraviolet light. The column is then placed in a water bath to maintain a constant temperature during testing. Nitrogen gas is applied to the column at 50 psi to represent overburden pressure in a sanitary landfill. Pressure is maintained until waste stops moving into the column. Standpipes are used to measure the rate of movement of the waste into and through the soil. Liquid effluent from the columns is collected in refrigerated amber glass bottles for measurement and analysis. After allowing sufficient time for the waste liquids to complete their movement into the column is then removed from the water bath and disassembled. The contents of the columns are then removed in layers, starting with the immobile waste fraction left on top of the column or waste top cake, and continuing with the underlying layers of soil. Each layer is placed into glass bottles and stored for measurement, analysis, or further testing. In a second set of experiments, a clean sand column is packed in the manner previously described. The immobile waste fraction from the first set of experiments is then applied to this column for leaching with simulated municipal waste leachate. This approach permits distinction between release in the primary leachate and release in the secondary leachate. The waste top cake is spread even over the soil surface and then covered with a layer of clean soil. This upper soil layer helps to prevent flotation of the waste components by the leaching media and also ensures that the leaching media is applied evenly across the surface of the waste top cake. A measured amount of leaching media is then applied to the column through the column top plate.
We conducted 2 types of soil column experiments. In the first set of experiments, we concentrated on the physical movement of the waste in the soil environment. We looked to distinguish between the mobile, liquid phase of the waste and the solid portion which stayed on top of the soil. The second group of experiments also included a leaching event in which we leached the solid portion of the waste with a leaching media that replicated sanitary landfill leachate. This leaching media is the same composition as that which is used in method 1311. One of the most interesting results in the first set of experiments was that although the waste moved into the different soils at different rates, the absolute amount that was mobile for the different waste did not differ significantly from soil to soil. In other words, the type of soil influenced the rate of movement, but did not influence the absolute amount of waste left on top of the soil after the experiments were over.
This graph pictures the percent of waste that was immobile in the soil column experiment replicates for each waste. The immobile waste fractions varied from 0 to about 75%, and the experiments were adequately reproducible, especially considering the heterogeneous composition of most of the wastes. Once soil column results were available, the average percent immobile results for each waste were compared with percent solids results obtained using method 1311. This comparison shows that the method 1311 initial filtration step, utilizing a 0.7 micron glass fiber filter, overestimates the immobile waste fraction for 4 out of 5 of the wastes tested. Thus, the current method can underestimate the release of toxic constituents in the primary leachate from certain difficult-to-filter wastes. Here, in a visual demonstration, Jeff Keever is performing the initial filtration step on a waste motor oil. Difficult-to-filter wastes also can clog the filter in the final filtration step, resulting in an inability to adequately separate the waste extract prior to extract analysis. Observe how much of this clearly liquid waste remained inside of the filtration apparatus above the filter.
This method, method 1311, has already been demonstrated to be adequate for a variety of wastes. Oily wastes were not included in this initial evaluation. So rather than to develop a new procedure for these oily wastes, we decided to see if method 1311 would work for the wastes, and if it didn't, see if we can make some relatively minor modifications to the method and still use the existing method. We looked at several different filtration step modifications to solve this problem. We looked at protecting the existing glass fiber either by a pre-coat of diatomaceous earth or sand, or by a pre-filter of coarse glass fiber, or as an alternative, a Teflon felt. We also looked at a very novel sintered stainless steel filter that has a different filter structure than all the other filter options we tested. These filtration options were tested and evaluated by comparing them with results from our initial set of soil column experiments.
This graph compares the soil column results with the results obtained with the diatomite filter aid, the Teflon felt pre-filter, the coarse glass fiber pre-filter, the multi-layer filter, and the stainless steel filter. The graph shows that for the range of wastes tested, the sintered steel filter estimated the immobile fraction of the waste observed in the soil columns more consistently than the other modifications tested. In this graph, the immobile waste fraction in the soil columns is compared to method 1311% solids results obtained using the 0.7 micron glass fiber filter and the stainless steel filter. Obviously, the steel filter offers significant improvement over the existing filter in estimating the immobile and mobile waste fractions in a landfill environment. The improved performance of the steel filter over the glass fiber filter is due to its unique structure. This illustration diagrams the structure of the glass fiber filter on the left and that of the steel filter on the right. During method 1311 filtration, waste is poured into the filtration device, which is then sealed and pressurized to 50 psi. As the waste moves through the filters, the waste solids remain on top of the filter and the filtrate drains from the bottom of the filtration unit. The difficult-to-filter waste clogs the glass fiber filter, leaving both solids and liquid on top of the filter. The steel filter completely filters the waste, leaving only immobile solids on top of the filter. The structure of the glass fiber filter is fibrous, with flow paths that are tortuous. Particulate matter can collect in these twisting paths, causing the filter to clog. The steel filter is composed of many small steel beads that are sintered together to produce a porous media structure that has straighter and shorter flow paths through the filter. This allows particulate and heavy organics to move freely through the filter media. This porous structure is similar to that found in the soil, which the filter is intended to model. This accounts for the close agreement between the steel filter and soil column results.
Once we had developed the modified method and were satisfied with the liquid-solid separations we were getting with the new stainless steel filter, we felt it necessary to evaluate the full modified method. To do this, we conducted the modified method 1311 in triplicate on the same wastes that we used for the soil column experiments. By comparing the waste constituents released into the filtrate and extract of the modified method with those released into the soil in the soil column experiments, we measured the accuracy of the new procedure. In addition, we conducted the existing method 1311 in triplicate to see how much we had improved on the results of that method with the modified method. Finally, the triplicate results from the modified method were used to calculate the new procedure's single laboratory precision.
Jeff Keever of RTI will now demonstrate the modified method 1311. This demonstration concentrates on the steps of the procedure that are different when the steel filter is used. The steel filter is to be used only for wastes that cannot be filtered through the glass fiber filter. Prior to use, the steel filters must be boiled in reagent water or otherwise de-aired and stored in reagent water until used. As with the glass fiber filter, the steel filter is mounted in the filtration device. However, because the steel filter is rigid, the support screen used for the glass fiber filter is not required. The filtration device is then assembled, the waste added, and pressure applied as in the existing method 1311. The initial filtrate is collected, measured, and stored for later analysis. The filtration device is then disassembled and the filtered solids are carefully scraped from the steel filter into a 2-liter glass extraction bottle. It is important to make this transfer as quantitative as possible. Once the solids have been removed, the steel filter is placed into a clean glass container and covered with 100 milliliters of the same extraction fluid to be used in extracting the waste solids. The container is then covered and the filter is put aside to be reused later. The appropriate amount of extraction fluid is added to the bottle containing the waste solids. As in the original method, the bottle is then placed into a rotary extractor and allowed to agitate for 18 hours. Following the 18-hour extraction, the original steel filter is placed into the filtration device. The liquid used to store the filter is added to the filtration device along with the extracted solids and extraction fluid. The extract is then filtered and analyzed as in the existing method 1311. The viewer is cautioned to include the 100 milliliters of extraction fluid used to store the filter when calculating method 1311 final analyte concentrations.
We have several interesting conclusions and quite a bit of very useful information generated from this project. First of all, by conducting our soil column experiments, we've provided some new information on how oily wastes actually move in soils and how the waste constituents may be released to contaminate groundwater if they're improperly disposed. Second, by comparing the results of these column experiments with the existing method 1311, we demonstrated that that procedure is not adequate for oily wastes and other difficult to filter wastes. Third, we developed a new procedure by modifying the filtration step of the old procedure that we feel is adequate and accurate, and we demonstrated its accuracy and precision by evaluating it again, comparing it with the column results.
Because the current method 1311 is adequate for filterable wastes, and because the stainless steel filters are relatively expensive, the modified method retains the glass fiber filter for wastes that filter satisfactorily through it. The steel filter is only to be used if clogging of the glass fiber filter is encountered. To recap, the current method 1311 is not accurate for certain difficult-to-filter wastes. Porous media stainless steel filters improve filtration efficiencies. The modified method 1311 is adequately precise and more accurately estimates release potential of oily and other difficult-to-filter wastes. For further information, contact Methods Section, Technical Assessment Branch, Office of Solid Waste, OS 331, U.S. Environmental Protection Agency, Washington, D.C. 20460. Area code 202-382-4761.